And I'm very happy to see that he rose up to the occasion. And as far as I can tell, he dressed up in a traditional Brazilian fashion. So the floor is yours. Thanks for preparing.
Yeah, thank you very much. Actually, some of you probably know that since many years I'm in love with Brazil. So I'm very happy being here in Natal again. And I'm also very happy that this project I'm talking about is done mainly actually in Brazil, mainly in Rio de Janeiro. So I thank you guys for working with me on that. And I'm happy that so many interesting things can be done in Brazil. This will be about mutual unbiasedness, which I believe in this community many people know what it is and why it can be interesting. So I will not spend much time discussing why to consider this sort of topic. Maybe I would tell you that the intuition behind mutual unbiasedness in general. I have this feeling very recently because now I'm more in the community when there are more people in classical optics, and for them they believe that not many things are quantum. People say, this is quantum, that is quantum. They say, look, it's many things are classical and they look perfectly the same. That's why I think being here I could also emphasize that fact because it's maybe underestimated. And this also pops up when you look at unbiasedness in the particular case when you have finite dimension, say D, in the finite dimensional Hilbert space, and you have two bases which are orthogonal. Then we define mutual unbiasedness only through this condition that the overlap between the bases is constant. It doesn't depend on the vector. You can take any vectors from these two bases and the overlap is the same. And again, this is Dirac notation. So one would say, okay, this is purely quantum, but these are only vectors. So this intuition you can track to other areas and places. Of course, this concept extends to several bases. You can have two bases, but you can also have 3, 4, and etc. For instance, if you have the simplest case of, let's say, a qubit, like simply the dimension is equal to 2, and you have the Pauli matrices, which all of you know very well, and the eigenbases of them, then they all fulfill this condition with D equal to 3 bases. They are 3 mutually unbiased, and this is the maximum number of this base you can have for D equal to. But what is important is that if you have larger dimension, you can have more bases. Sometimes you can have D plus 1, for instance. So it's not a limitation. You can have many bases in the discrete case. Now we go to the continuous one, and in the continuous one, it's always said that portion and momentum, they are mutually unbiased, even though these vectors might not be well defined, let's say more mathematically, because we had a mathematical presentation quite like before. And okay, so in the continuous scenario, we have these vectors. We have two-wave functions, which are usually related by the Fourier transformation. What is really interesting, and this is something which not everyone knows, is that when one considers the same thing on the phase space, so not only x and p, but we have the whole phase space and any direction which is parameterized by an angle. You can have any of that. The question is how many bases are mutually unbiased. One could think maybe infinitely many because the dimension is infinite for this Hilbert space. In fact, you can have at most 3. You can have, if you take portion, you can have 2, say, symmetric directions, and that's it. You cannot have more. I find it interesting because this distinguishes the discrete case from the continuous. In the discrete case, you can have many bases which are mutually unbiased. In the continuous, these are only 3 bases of this specific form. Okay, let's go to the questions that I would like to answer today in my talk. First of all is that we have this continuous case and we have the discrete case, and they are completely different. And what we found interesting is how to impose this finite dimensional mutually unbiased structure into the scenario with continuous variables in a way which is faithful. Faithfulness is very important because if you don't care about that, this is a rather easy task. You take a continuous variable, expand in modes, select 2 modes, discard the rest, and you can play with that. And in this way, you can try to implement, as these are discrete systems, but you need to discard a big fraction of the information. The question is whether one can do this without losing the information, but rather taking care about the whole content which is in the continuous variables. Another point which is, I think, always important is that something we can do is experimentally friendly, that you can really implement, make a measurements, and show what you derived. The second question is, which I already told you, is that what is the message carried by the number of mutually unbiased bases in general? Because we see this difference. In continuous is maximally 3, in discrete is something more. If we try to impose the discrete structure on the continuous variables, we can think, what is the number of bases and how does it relate to this? What are the insights? So these are the questions to be answered. And now it comes the slide which is the most dense and the most difficult. So if we go through that, I think it will be only smoother. And what it presents the structure we consider, which will be the coarse graining. This will be periodic, but that's something we presume. You will see in a second. In the most general case, what we define two sets of projectors, finite numbers. So KL goes from 0 to d minus 1, so it's only d projectors for position and d for momentum. And they are constructed in a way that you have some, let's call it mask function, which is not negative. It should be normalized in a way that it's all masks, they sum up to 1. They can be centered at some particular value of the coordinate, and they will depend on some coarse graining parameter, which we call the period, because that's what we presume. But in principle, you can consider any other sort of functions playing this role. What we consider particularly are these periodic structures, which are, you take the variable, divide into periods, and since you have the dimension d, you divide the period into d pieces. And that way you construct d functions. So the first function takes only the first part of the period, the second would take the second one, and so on. In this way, you can cover the whole line of a variable with this, I would say, rather basic scenario. So what is the parameter of relevance is the, let's call it slit width, or experimentally, which is the period divided by d, so the dimensionality of our structure. Okay, more formally, the mask function is defined like that. So it's 1 in this particular regime, and is 0 elsewhere, and j tells you in which place this is 1. For instance, if you take d equal 2, you can have two masks. So the first one, white, means that it allows the light through, so it gives the value of 1. And the second part of the period is 0. The second mask is the other way around. If you have d equal 3, you have 3 options, which you see the symmetry which appears in the structure. Okay, now we can discuss mutual unbiasedness. You will immediately recognize that in this case we cannot talk about the standard way because there are no vectors, there are no cats. Like in this Dirac notation, we have projectors. But actually, I would not understand why this forms a problem, because unbiasedness is a concept which has a more general information. It tells you that if you have two sets of probabilities which come from something, and your distribution is localized in one set, so it's 1, 0, 0, 0, 0. And then you look at the second distribution. It needs to be even. If this is the case, and it works the other way around, if you are concentrated here and this is even, then this is unbiasedness, because knowing perfectly the one, you know nothing about the second one, and vice versa. And it doesn't necessarily need to be that what creates the distribution is a projector of rank 1. It can be any projector, and it works the same. If they are POVMs, it's not so easy because of the, say, normalization, but for projective measurements, it's the same like for the vectors. So this is our definition of unbiasedness, which I think it's fully legitimate. And now we can go to the major result. The question is, we have these two structures, in portion and in momentum, and we want to ask when they are mutually unbiased. And the criterion for that is quite simple, and I find it has some beauty. It's symmetric, it involves both periods and the dimensionality. So if there is a relation between these parameters with which we can play with, there is some extra natural number which gives extra possibilities, then we have this property of unbiasedness. The thing is so simple that actually we can even look at the proof of that statement, which I hope you will enjoy. Proving this, we start with the mask. Let's say the plot is for M0, but then you have this K which labels the mask, and you Fourier expand this function. When you Fourier expand, you always have 1 over D, so the target we have, and some other infinite series which contains several oscillatory terms. And now, let's focus on the momentum probability distribution. So we have the state, and we have the momentum projectors, which are like this, I shown before. And the question is, how does this object look like if we transform to the Poisson representation? So not the momentum wave function, but the Poisson wave function. And when you do this, using this formula, of course, 1 over D remains because this is a constant. But this term, and particularly that piece, it creates autocorrelation of the wave function. So you have several terms which all autocorrelate different areas of the wave function. Now, if you include unbiasedness through the condition, this means that somehow in this autocorrelation term, almost always it happens that piece which is here non-zero, it always faces piece here which is 0. And this is 0 because the distribution is localized, because that's what we test. So almost always this autocorrelation gives 0 because you take different pieces of the period. Only sometimes you can find in a different period the same part of the slit, and then this is non-zero. But in this particular case, there is a term, because it depends on n, which always cancels. This is always 0 in this case. In other words, in all the situations, all the terms, they do vanish, and we have only 1 over D as a result. And that's the idea behind. I also like the experiment because it's really intuitive, and again, I enjoyed the fact that being like the meeting with people working with quantum optics, I could show this, and for them it was perfectly fine because that's what they do and understand. So exactly, because what it uses is the analogy between paraxial optics and quantum mechanics. And this is really interesting because for many people this means that basically no effects are quantum. I'm repeating that because I hope that there might be a discussion about these things, because this is something which I find interesting, that so many people in this optics, especially classical optics community, they say, look, this is not quantum, this is all like wave mechanics, like, and so on. And experiment indeed is not quantum because it's for a single light beam. So what is done, there is a light beam, there is special light modulator which creates the mask and prepares the state which is localized in a particular piece. Then there is a Fourier transform setup and another mask which scans to all these possibilities. So in this way, in this piece, you can create a state which is localized in the first set, and then here you can scan whether the distribution in the second one in the momentum is even or not. And indeed, the experimental results, they show exactly how it should be. Namely, maybe now I will go back to this number m, which was a few slides before. Maybe I will even go back. There is this natural number here, and this cannot be an arbitrary number. For instance, if m is equal 1, this is the basic case, and then for m equal 1, it always will work if the condition is fulfilled. On the other hand, m cannot be equal to d, because if m is equal to d, then this defines, it's called commuting periodic sets. So one has these modular variables and all these things, but in principle there is full commutation, so there is no room for unbiasedness, because then if one degree is perfectly described, the second one is also perfectly described. There is no way of even distribution. So depending on this value of m, there can be like unbiasedness or something completely opposite, and it really is shown in the experiment when we have d equal 4. If we have d equal 4, we can have indeed 4 values of m equal 1, m equal 2, and so on. And m equal 1 and m equal 3, or looking at the distributions, this is this unbiasedness. and then the distribution is indeed even as it should be. If m is equal to, there is no place for unbiasedness because there is a partial concentration in two values of the degree of freedom. And in m is equal to 4, this is this periodic commuting set. And then there's a perfect localization also in the second basis, assuming this was localized in the first one. All right. What we can do further, we can extend this whole formalist to the phase space. And the extension is quite natural. Instead of the Fourier transform, you have the fractional Fourier transform, and you can rotate from the position to any other angle on the phase space. And the condition which one obtains is really basically the same. It only has the difference of the angles involved additionally to the rest, which is not surprising. Normally, if this is equal to 1 for positional momentum, this is the case. But if they are closer to each other, then it somehow needs to be emphasized. There's a thing I like very much, and I'm always emphasizing this because I'm waiting that someone tells me that at least he or she found a better result, namely that I don't know how it was possible and how it happened, but we somehow managed to publish this in 1 month. Exactly. From the 4th of April when it was received till the 4th of May when it was published. It was accepted 18th of April, so even they spent like 2 weeks in the production process. I don't know what they produced, but this was like that. So whenever, no really, because the changes at the end, they were very, very minor. Like there were a few like language comments and that's it, but they kept it like 2 weeks almost. So whenever you have or whatever the paper which has like similar record, please let me know because I'm really interested to have this in my file and show together with this. Okay, but going to the topic, if you consider now the same problem on the phase space, and particularly focus on these 3 directions which were shown before on the phase space, so the special directions, you can basically do the same and show unbiased in the same way. So one can confirm, and this works exactly the same way as it should. Now there comes the second question, which for me, I like it very much, is that if we have the structure of unbiasedness, we can now ask the question how many mutually unbiased measurements can be admitted by the phase space for a given dimensionality. We remember that in the discrete case, the number can differ from the dimension, can be d plus 1, maximally can be something smaller, sometimes it's not known, etc. In the continuous case, it's always 3. And now what we have here is the discrete structure imposed on the continuous variables. So the behavior of how many mutual unbiased measurements of that kind can be there is not a priori clear. It might be more continuous, might be more discrete, might be something in between. And in fact, what we found so far is quite interesting. So first of all, we have these conditions, which now if we have several bases, we can have several natural numbers in this scheme. So we have a huge degree of freedom, in fact. What we know is that if we set all these numbers m to 1, so we consider the basic scheme in every direction, then we can have at most 3 mutually unbiased measurements in the scheme, exactly like in the continuous case. Moreover, what we know is that if d is an even number, so the dimensionality is even, we can only have at most 3, like in the continuous case. Finally, what we know is that if d is odd, we can have more than 3. We don't know yet how many, maybe d plus 1 maximally, this needs to be shown, but for sure we have this is more, and this has a consequence because this dimensionality d, one can think about this d like being large as a limit, as a continuous limit. You have a discrete system, and you have d to infinity, and this should be continuous. And indeed, when you look at these masks and so on, they can fairly well reproduce the continuous distribution. This is not a problem. But such a feature like this unbiasedness will not be reproduced in the uniform way, because even though for each d even, this will be 3 like in the continuous, it will always jump for some odd values. So the limit, at least in that particular feature, does not exist, which I like very much, because This is the same which happens with the uncertainty relations. You have some uncertainty relation in the discrete system, and it's always saturated in a way that in one case the probability distribution is 1, 0, 0, 0, and in the second one it's even. This always happens. But when you go to the continuous case, it cannot be. Or maybe you say you have the Dirac delta and the flat with the value of 0. This is the limiting case, but in principle it cannot be. So then there are Gaussians which pop up suddenly because they are not there in the discrete, and in the continuous they are. So the limit is not well defined, and this is yet another feature which shows this. Okay. I'm always prepared for the fact that there are some delays, and that's why I prefer that I don't use the whole time. I always schedule it for a bit shorter because then there is more time for discussion and the break and so on. So it's actually the time to summarize. The first point is that what we have the mutual and biased measurements for the continuous variables which have finite cardinality. So it's not infinite dimension, it's the dimension d, and you select. It can be d equal 2, equal 3, 4, 7, whatever, and you can always select the parameters of the periods in such a way that it works. From the conceptual point, this can show another sort of links between the discrete quantum mechanics and continuous quantum mechanics. The last message which I tell to everyone is that coarse graining is there anyway. If you consider the experiment, then the coarse graining is there, so there is no reason to abandon this. Rather, you can say, okay, if we have this coarse graining, why not to consider schemes which use coarse graining to benefit from it? And benefit is, as I also said before, is this faithfulness, because you have mutual unbiasedness, but you do not discard the information. Maybe practically you can say that you assume that your state is in the lab. It doesn't go beyond the lab. Maybe this is an assumption. But apart from that, it's fine. You collect the whole information. When in other schemes, when you really need to pre-select the fraction of modes, you discard the information. I understand that when people work with optical angular momentum and they select 100 of modes, then I can believe that sort of they contain the whole major information of the system. But if they restrict to 3, I don't believe in that. There is always something which needs to be discarded, and this has influence. For many things, also for QKD. I think that this scheme in particular can be useful in QKD, but this also one needs to work out better in the future. Okay, thank you very much.
Yeah, science of light indeed. Thanks for this very nice presentation. We have plenty of time for